Single slit diffraction. Double slit interference made sense since each slit became a new point source, like that, and then these waves interfered with each other. However, when you have one slit, a single slit, that has a width on the order of or a little greater than the wavelength of light going through it, you also get an interference pattern. As you would imagine, there is a wide, bright central maximum. However, what is strange are the secondary maxima that appear after dark minima. The main bright spot is right in the center, but what is interesting to us is the location of the first dark spot. We can use the same trigonometry as before, but this time let's focus on the first dark band. Let's analyze what's happening. If we divide the whole slit into two halves, we'll have the top and the bottom. So this is not two slits, this is just one slit, but just so we can figure out what's happening here, imagine dividing it in half. All right, so Huygens principle, which states that every wavefront is actually an infinite line of point sources. So we can draw like an infinite number of point sources all the way down here. Technically, this is not infinite. I think there's about 12 of them. But let's focus on just the very bottom point source and the one right at the midpoint. Those are both in red. At this exact angle, the extra distance traveled by the bottom wave here is going to be d over 2 sine theta. So this wave is going to be 180 degrees out of phase with this wave. So the extra distance traveled by the bottom wave is d over 2 sine theta, because this is the same trig we were doing earlier. And so this is like having the extra half of a wavelength further than this one, which means they're now out of sync, which means this light ray right here and this one are going to cancel out by the time they get to the viewing screen. The points in green, the one right above that and then this one right here, those will also cancel out since the green ray has also traveled exactly that same extra distance. So those will also cancel out. So every point source here is going to cancel out with the one above it, the corresponding one above it. So at this very particular angle, every wave coming from every point source cancels out completely with another one. This is why there's a dark band at that exact location corresponding to this angle. The same equation used to find the bright fringes in the double slit experiment is now used to find the dark fringes when solving single slit interference problems. But be careful. This time, little d in this equation represents the width of the slit. For double slit diffraction, d represented the distance between the slits. But you're going to use that same equation. Just remember, now with a single slit, it's going to tell you the location of the first dark spot, or the second dark spot, or the third, depending on the m value. The width of the central maximum in single slit diffraction is 2 lambda over d. As d gets smaller, so as the slit gets narrower, the central maximum becomes wider. As the slit becomes narrower, the light diffracts more. As d gets larger, so as the single slit gets larger, the width of the central maximum gets smaller. The width of the central maximum is important for optical instruments, including our eyes, as it limits how clearly we can see. Simply having an aperture, like a hole or a slit, means that the image of every object projected onto the screen, like a film, a sensor, or your eyeball, will have some spreading and fringes, however slight. The smaller the aperture, the greater the spread, so the less clear an image, and the more it might overlap with the images of other objects, the less we can resolve one object from another. That's why an eagle's eye is so large, why large lenses on cameras give better pictures, why telescopes have to be large, etc. As the size of the aperture increases, or the slit, so does resolution. When the slits in a double slit experiment are much smaller than the wavelength of the light, the purple plot results. So that's these lines here. All the maxima are the same height. For single slit diffraction, where the width of the slit is a little greater than or on the order of the wavelength, the light blue plot results. Here, this plot. An intense central maximum and less intense maxima as the order of the maximum increases. So you see this just small maximum right here. When the width of the slits in a double slit experiment are a little greater than or on the order of the wavelength, the dark red plot results. You can see that here. A combination of the point source double slit interference and the single slit diffraction pattern. The single slit diffraction acts as an umbrella function, compressing the double slit pattern. In addition, some orders disappear as the minimum of the diffraction pattern overlays the intensity of the double slit pattern. In a single slit experiment, the width of the slit is 1.8 micrometers, and light of wavelength 480 nanometers passes through and strikes an observation screen 0.92 meters away. How far is the first dark fringe from the center of the screen? Since this equation is not on the AP Physics 2 equation sheet, let's quickly derive it again. So we have a single slit experiment. This distance here is L. This distance here to the first dark band, so we have like a dark band, central maximum, like that. This distance from the center is x. Here is theta, and due to small angle approximation, we can say that tan theta is approximately equal to theta, which is equal to opposite over adjacent, x over L. The equation that is on the equation sheet is d sine theta equals m lambda, which not only gives you the bright spots in a double slit experiment, but it gives you the dark spots in a single slit experiment. So we can replace sine theta, which is also approximately equal to tan theta, which is also equal to theta when you have a very small angle. So we can replace sine theta with x over L. So d x over L equals m lambda. Solve this for x and we get this equation here. At that point, we can substitute in the givens. Since it's the first dark fringe, we put in a 1 for m. We have the wavelength of the light, which we've converted into meters. We have the distance to the screen, 0.92 meters. We also convert the slit width into meters from micrometers, and we get 0.245 meters.